welcome back. So today we will look into bounded model checking. Earlier we have seen model checking where we have seen temporal logic, temporal operators, and then competition tree logic, and we have seen how we can evaluate some property on Kripke structure. But when we talk about the bounded model checking, we evaluate the evaluate the properties on the Kripke structure using satisfiability solver. The way we can actually verify a property on a Kripke structure, we need to restrict the path length that we will be looking into in this lecture. Since we need to restrict it into path length, therefore we need to have a special bound on that path length, and this is usually referred as the bounded model checking. So we will see more on that part. So uh, so the broad idea for the bounded model checking is that we construct a Boolean formula which is satisfiable if and only if the underlying state transition system can realize a finite sequence of state transition that satisfy the temporal property we are trying to validate. So the idea for this bounded model checking and the model checking that we have seen earlier is the same. So that is the basic idea. We just need to construct a Boolean formula and we have to verify that thing, and rest of the stuff remains same, that we will be provided with some Kripke structure and we need to check the temporal property. Only thing is that we are not going to look into the infinite sequence but a finite sequence of the state transitions, and this will be done using SAT solver, and so which is actually which is nothing but the satisfiability of Boolean formula. So our target will be to construct a Boolean formula using the Kripke structure, using the temporal property that we want to verify, and we need one more information in order to construct that Boolean formula, because I cannot construct a Boolean formula of an infinite length, so I need to make restriction of that length, and which is comes as a as a bound. We will see more on that part. So what happens? So we assume a path bound, let's say k, and then we try to verify up to a path length k, and if it is being verified, then it's well and good. If we cannot comment on that part, then what we do, we increase the bound one more step, and then we try to verify. Because what may happen, that if a property which is not verifiable, say up to path length of 3, but if we increase the path length to 4, the property may be satisfied. So what we need, so the basic idea is we increase the path length, we gradually increase the path length, and we check for the satisfiability of that one. So so this bound can be increased incrementally, that we are talking about, and until we reach the diameter of the state transition graph. So once we reach to the diameter, then it's complete. Otherwise, and the problem is that we do not know that diameter, because this if we know the diameter, that means we have the complete state transition system with us. Sometimes the state transition system will not be provided explicitly to us. We will not be provided explicitly to us, because it is the this state transition is we need to extract out from a given circuit, because finally we are trying to verify some property on a some sequential circuit. So from the sequential circuit we need to extract out this state transition relation, and therefore we do not have the idea about the diameter of the graph. So what is the diameter? So you can find out the diameter of a graph when you have the complete graph to you, complete graph given to you. So you just find out the shortest path between each pair of vertices, and then you choose the greatest length among all those paths. So that will be the diameter of the graph. So what is the requirements? Then definitely we need temporal logic or the temporal formula which we would like to verify, and we would like to verify over a Kripke structure which may be represented M, and a bound on the path length K, and this is the new addition for bounded model checking. So what we do here in bounded model checking, only path of bounded length K or less are actually considered to check the satisfiability of the temporal logic of the formula given. So what we do, we in order to check the validity, what we do is we translate into a SAT formula. So what we need to do, we need to unfold the property into Boolean clauses over the different time steps. So this formula that we have been asked to verify, it will have temporal operators. So we need to unfold that temporal logic or the temporal formula over the time steps, and for every time steps we'll be allocating one Boolean variable. We'll see with an example. So this is for the temporal formula that we need to check. We need to unfold the state transition system or the state machine. So the state machine that have been given, which will be again which will be usually expressed as a Boolean logic, that we will see how to do that. But the state transition that I have, we need to unfold that state machine over, over the same number of time steps that we have done for the temporal formula, and then we check whether the clauses are together satisfiable or not. So we will get a set of clauses by these two things, and then we would like to verify that these clauses are satisfiable together. So we are talking about the unfolding of the system. So how we can do that? So the example that we have seen in the model checking is a simple example. So we have an arbiter. There is two requests that can come, R1 R2, and we have two grant lines, G1 and G2, and one of the very simple query that we can ask, or we can say that if R1 is true in a cycle, then G1 has to be true for the next two cycles. And if you want to express this property in a formal manner, then probably I can represent that R1 implies in next G1 and next G1. So you are not writing it the complete CTL. So just in order to highlight the unfolding of the system. So this property definitely represent the stuff that has been described in English. Now when we do this unfolding, and once we do this unfolding, for every time step we assign some new Boolean variable. So initially at t equal to 0, we have these 4 Boolean variables. In the next time step again we have another 4 variables, but all belongs to the same stuff. So this is r1 at t equal to 0, again r1 at t equal to 1, and we distinguish these variables over time by introducing another index time to the variable. So which we would like to express in this manner, that this is the r1 variable at time instant 0, this is r2 at time instant 0, and so on and so forth. Now when we do this unfolding in the next time step, we'll again have the same set of variables r1, r2, g1, g2, but now we will introduce, we have already introduced the time index variable. So this actually distinguishes the set of variables from the other time steps. Similarly, we can proceed for every time step. We allocate those Boolean variables and we continue to do so. So now when we have this temporal property and we would like to express, then we have to use the variables across the time steps. So in this case, what we can do, if this property we would like to check, then we can say r10 implies that g11 has to be true and g12 has to be true. So we can express in this manner. So in a more generic form, we can write a condition, or we can write a set of clauses that r1t implies g1t plus 1 and g1t plus 2. So this is for any time step, this should hold. So we can write the set of clauses and we have to check for the satisfiability. Now quick recap on CTL. So we looked into CTL. So we have two path quantifier, always and existential. We have the temporal operator like the next, future, global, until operator that we have seen, and we have seen the complete stuff. Like, just to elaborate, there exist or EF started and not ready, which actually means that it is possible to get to a state where started and not ready both holds. Similarly, if AG request implies AF grant, so which means that if a request comes, then it will eventually be granted. Now we'll look into symbolic model checking. So we said that we allocate the Boolean variables for we allocate the Boolean variables for the temporal formula as well as for the state transition system. So how we do this for the state transition system, that we will see here. And before we go into that, what we need to do is that we need to extract out the state transition system from the actual circuit implementation, because we will not be provided with the Kripke structure directly or the explicitly, because when we verify some property, I will have the get level representation of the circuit and the property that I want to verify, and this get level representation it will be a sequential circuit. From these sequential circuits, we need to extract out the transition system, and we extract out this transition system in a symbolic manner. So how we do that, we will be explaining that thing now. So in order to do that, what we do, we we allocate Boolean variables for the present state of the latch and the next state of the latch and as well as for the input variable. So you can easily understand that in order to represent the transition behavior of the system, I need to describe the next state function or the next state behavior in terms of the present state and the primary input that are available in the system. So what we do here is, so in a sequential circuit, what will happen, I will have a set of latches in my design. So let's say this is some latch or the flip-flop. I have some input, and this is my output. So effectively there will be a combination logic here which I am not drawing, and there will be some primary inputs coming to here. So if this is the present state, let's say S, and this will be my next state S prime, and this S prime is getting updated at the edge of clock, and we implicitly assume there is a clock, and we do not use this clock in our representation. Fine. Now in order to extract out this transition system, what we do, for every latch we allocate Boolean variables for the present state and the next state, and this function or this present state that we represent through this S, this will be function of the primary inputs and it can also have the so this S will be a function of the primary inputs, as well as it can also depend on other state input. So what we can do, we can write an expression involving S and S prime, and this S is a function of the set of states. Let's say I call this as X, and the set of primary input variables. So that is the stuff that we have written, and this Boolean expression that we have not written anything, the combination logic, it will be represented as a function fi. So that's the sum that I have written. So we compute Boolean expression fj for the input function for each latch j in the circuit. So we compute this functionality, and let us assume this x is the present state vector and I is the primary input vector. So in order to write the state transition system, we can actually claim that these two values, this value of S and the value of S primes, are the same, because whatever S prime I am describing here, it is nothing but the S that was there in the previous steps. So the transition relation for each of the latch will be represented as in this manner. So which says that the next state variable is next state variable is nothing but the same as this functionality, because this value will be updated at the edge of clock, and the functionality that X prime will be observed is nothing but the combinational input to that latch. So this symbol is means it's a if and only if, and it's nothing but the XNOR function that we have seen in the Boolean logic. So this is with respect to a single latch. So the transition relations for a single latch will be this one, and if we and for all the latch we just need to do a logical AND of all those latches. So if the transition relation is TS to S prime, so T of S and S prime, this S and S prime denotes the present state and the next state, then we can actually say it's nothing but the logical AND of this transition relation for all individual latches. So the thing is, once we have this stuff, we can actually convert it into SAT, because this is nothing but a Boolean expression. So this Boolean expression can be converted into CNF form, and we will see later part of this lecture how to convert this thing into CNF form. So now we know that given a circuit, how we can actually construct the transition relation. And just to highlight that this transition relation will be computed in a symbolic manner. So this is nothing but a Boolean formula. And interesting thing to highlight here, that the Kripke structure that that we have looked into earlier is typically represented in the explicit manner. That means I have the complete graph. Now I am representing that graph as a Boolean expression. So it effectively means like say let's say I have a Kripke structure something like this. Say I have, let's say, 3 nodes, and let's say this is S1, this is S2, the state S2, and this is, let's say, S3, and this is, let's say, this is connected and this is connected something like this. Now this transition relation that we are expressing in the as a Boolean expression, let's say we would like to express this transition relation as a Boolean expression. So what we need to do actually, we need to encode the states as a binary string. Let's say we represent the state S1 as 0 0, this is as 0 1, and this say this is 1 1. now to represent this relation, what we can say, that when I have a present state as 0 0 and the next state is 0 1, then I have a connection. I represent that when this present state is 0 0, that means it is in S1, and the next state is 0 1, then there is an edge. Similarly, for this edge I can represent as when it is 0 1, and when the next state is 1 1, then my output should be 1, and similarly for this edge. Now if you look into this table, this is nothing but a truth table that I have, and I can construct a Boolean function or the Boolean formula that will produce 1 as an output when these conditions are satisfied. So effectively we are translating this transition relation as a Boolean expression. So given this graph, I can translate into a Boolean expression in this manner, or I can extract out the Boolean formula or the Boolean expression for the transition relation by using this method from the actual circuit. Now once we have this transition relation, we need to do a traversal, because unless we traverse on this transition relation, we will not be able to figure it out whether the properties is satisfiable or not. And interesting thing is that on this Boolean expression that we have computed, we can do the binary operations, we can apply certain operations, and we can do the actual traversal. And this idea depends on primarily two things: the computation of images and the pre-images. So what is images? Images is the successor and the predecessor of the states. So if I am in this state, I would like to find out the set of state from where I can reach to this state. So let's say the state of interest is this one. So if this is the state of interest and I would like to compute the pre-image, then this is the set of states. This is one of the state, this is another state from where I can reach to state S. So the pre-image of S will be these two states. Fine. And similarly, if I compute the images, then I just need to find out the successor of S, which may be these two states. So this is the pre-image and this is the images of the state S, and this can be actually computed using Boolean operations. So let's say we have been given a set of state PS. Fine. And we would like to compute the set of states that are reachable from the given state. So that means we have been given this S and we would like to find out these states. So what we need to do is definitely we need to use the transition relation. So if we think of this transition relation as in this manner, so this is a truth table which basically signifies the present state and the next state for which there is an entry 1. Now when we would like to compute the images, that means the set of state have been given to me, the present state, and I have the transition relations. So on the transition relation, I would like to choose those rows in which PS is satisfied. So I'd like to choose those rows on this transition relation in which the PS is true. So this will give me only those entries on the transition relation where PS is true. So now what we need to do, so what we will get? We will get this PS and the set of next state, but the Boolean expression that I will have will involve both present state bit and next state bits, because in this expression T and P, this will have both present state and the next state. Now we would like to find out only the next state. So what we need to do, we need to existentially abstract out, or we need to drop the state bits from this expression, so which we call the existential abstraction. That means that I just in a very simple sense, that I just do not want to bother about S, I just want to bother about only the S prime. So I just existentially abstract out. So it effectively means whatever may be the value of the present state, I just only I just want to figure out only the next state. So which can be expressed in this manner. So if I have a Boolean expression something like this, and I want to drop, or I want to do an existential abstraction, then mathematically it is defined as these two Boolean expression. So effectively I replace the Boolean formula xi with 0 and xi with 1, and then I do a logical OR. So it effectively means that whatever may be the value of xi, I just do not want to bother. So irrespective of the value of xi, I would like to find out the Boolean expression. So that will give me the image. Similarly, when we want to compute the pre-image, we can apply the same strategy, only the set of state that we are talking about, that has to be treated as the next state. Now on this table, on this transition table, if somebody provides me the next state, and if we do the same operation like ps prime and t, that will give me the set of rows in which the set of rows in which the next state will be provided by ps, and I can reach to that state from this set of present state. And our interest is to find out this set of state from where I can reach to the given next state. So it's effectively the same steps, only thing is the way we interpret this one. In the when we compute the image, we treated ps as the present state. Now we will be treating this ps as the next state, so therefore we have written as ps prime. Now once we have this Boolean function, the transition function, and let's say we would like to verify this property EFP on a on a transition relation. So let's say the set of states, so we would like to check EFP. Let's say Q be the set of states in which P is true. So what we used to do in the explicit model checking, that when we would like to verify EFP, what we do, we first find out the set of state in which P is true, and then we would like to find out the set of states from where we would like to find out the set of state from where I can reach to this set of states. So if there is a state in which P is true, then I know EFP is true, and I would like to find out the set of states from where I can reach to these states. Then I will also tag EFP on these set of states as well. Let me call this as X. So if P is true, then I can say X EFP is true here, and if I can reach to this state from the set of states here, then EFP is true also here. Similarly, if we have another, if we can reach to any one of these states, then I will also say that X is true here. And we just do not, one thing, we do not need to look into this path, because if I can reach to this state in a single steps, then these have been already included here. Only thing I just need to check that whether I can reach to the next state from to whether I can reach to this set of state from this one in a single time step, and so on and so forth. So we'll be doing the similar thing here. So we start with this we start with this set of states that will be an input for us in. So this is the set of states in which p is true. Fine. So let me say that this set of states is the q, and we initialize this thing with this is as r as well. Now what do? We compute the pre-image of q. So this is the set of states. That means this is the set of states that are in which EFP is true. We just need to find out the pre-image, because in all those pre-images, the set of states that belongs to the pre-image in which EFP will also be true. So we compute the pre-image and let us call this as pre. Fine. So the thing here is the set of state in which EFP is true is actually this set of states. Now that we have figured out when we apply this pre-image one time, and the set of states in which EFP is true is these two set of states, and which we will be using as the union reached. So in this set of states, my EFP will be true. And if we reach a situation when this union reach, that is the blue one, is same as this R1, which basically stores the set of states in which EFP is true. If these two set of states are the same, then we know we are not exploring any further, even if we allow few more time steps. So this variable r is just used to track that in the two consecutive time steps we are not exploring any new states, and at that point of time we can actually break from this loop. Fine. So this is the stopping criteria, and what we do, we find out the new q now, and this new q will be this set of states that we want to figure out, which will be nothing but pre and not r. So not r will encompasses all of these states, and this r will be updated with this set of states, and it will keep on repeating the stuff. And once we reach to a situation that we are not finding out any new states, we just stop and we do the checking whether this is actually satisfiable or not. So here we need to do the set of states in which EFP is true in this case, and the initial state, this is satisfiable, and if this condition is satisfiable, then we can say that EFP is true. We can find out the set of states in which EFP is true, otherwise it does not hold on any one of those states. So this is the generic idea for symbolic model checking. Now when we look into the bounded model checking, or when we need to convert into a satisfiability model, what we need to do, we need to construct a propositional formula for the Kripke structure and the formula, and there will be a bound k. So I just need to unfold or unroll the formula and the test transition system up to k times. So the unroll transition system that we can actually specify as in this way. So I start with h0 and I apply this transition rule k number of times. So this will give me the state transition relation. So Si and Si plus 1, and I have to do a logical AND of k number of timestamps because we are unfolding for k number of times. We'll elaborate with an example, and similarly we need to check for this this formula A on a path length of k whether it holds or it does not hold. So we need to unroll that thing too, and once we have this clause, once we have this stuff computed or the unrolled system, what we need to do is we need to do a logical conjunction between this and this, and we can actually figure it out whether it's satisfiable or not. We have to check the satisfiability of that big expression. So let's say we would like to consider the CTL formula EFP, and we would like to check whether EFP is can be verified in 2 time steps, or we would like to check the validity of EFP with 2 time steps. So that means k equal to 2. So if I want to check this one, then what I need to do, I need to unfold the transition relation for 2 time steps. So I have computed the transition relations or extracted out the transition relations from the actual circuit. I know the initial state, and in any one of those states I just need to check whether P is true at S0 or P is true at S1 or P is true at S2. So if P is true in any one of these states, then I can say that EFP is actually true at S0, or the initial state it will actually hold. So let's take an example, more concrete example. So let us say we have a 2-bit counter with least significant bit we will be representing with Boolean variable A and the most significant bit by B, and let's say it follows this transition relation. So 0 from 0 0 it goes to 0 1, then it's 1 0, then it's 1 1, and it keeps on repeating, and 0 0 is the initial state. So we can actually create a circuit that can represent this 2-bit counter in this manner. So the least significant bit gets toggled at every clock, and this Boolean functionality for the second latch will be A XOR B, that you can actually figure it out. So given this transition relation, we would like to check whether we can reach to a state 1 1 or not. So let us assume that initially both the bits are 0, and we used to check whether we can reach to a state in which to a state in which 1 1 will actually hold, or maybe I can say that A is 1 and B is 1 at that state. So does there exist any such state, so which we can represent as EFP, and P is nothing but A and B. Fine. So what we need to do, we need to unfold the transition relations, and we have to check for the reachability. So and we said that the initial state is 0 0. So we start with the initial state, that is the initial state is 0, and at S0 this is being held. Now we have to unfold the transition relation. So when we unfold the transition relation between S0 and S1, this will involve the variables A1 and A0, similarly B1, which depends on A0 and B0. So this is the transition relation at time step 0, and similarly the transition relations at time step 1 is this one. So we are unfolding up to 2 time steps, we are not unfolding more than that. And what we would like to check, that whether these conditions is being satisfied in any one of those steps. So if I have a path length of 2, then it can have at most 3 states. So I would like to check whether this condition is being satisfied at S0, or this condition is being satisfied at S1, or this condition is being satisfied at S2. If this condition is being satisfied at any one of these states, then definitely I can say this property holds at this state. So I have to check the validity of this Boolean expression, and how to do that with set we will come back. But the main point is that we construct this Boolean formula and we just need to check the validity of this formula. Now one thing to note here, that if it's valid, then I know the property is valid. But if this is unsatisfiable, then what does it actually mean? It can mean the property is not verifiable, or it does not hold, or that can be one option, or since we have unrolled for 2 time steps, therefore it is not satisfiable, but if we unroll for few more time steps, it may be satisfiable. So when it answers that it is unsat, that means it's not satisfiable, then we cannot actually guarantee, or we cannot say that it is really unsatisfiable or the property does not hold. So therefore so whenever we say it's satisfiable, then it's okay. If if I get an answer unsatisfiable, we cannot we can only say that it is not satisfiable up to a bound length of k. Now let us look into this property AFP. So we use the similar transition relation, only thing we add one extra transition from 10 to 10 itself. So the transition relation that we will have will be same as before, which is the basic transition relations, and along with one extra transition. So if I am at 10, then I make a transition to 10 itself. So the complete transition relation for this new diagram will be this one. And what do we want to do? And we want to check that whether we eventually reach to a state where I want to reach this state 1, 1. So if you look into this diagram, then you can easily understand that this is not satisfiable, because I can have a path something like this, and then I am just loop back here. So it's actually not satisfiable. And how we can answer that thing, that we have to see. So we would like to check whether we can make a transition, eventually we can make a transition to 1, 1. So in order to verify this property, we use this expression, because using the duality we can express this a p property as egp, where p will be nothing but the negation of this property, and if you want to make it equivalent, then if this property holds, then this does not hold, so there will be a negation. Now let's say we would like, so in order to verify this one, we would like to check the validity of this property, and that property would like to check for 2 time steps. So all candidate paths will have 3 state as before, so initial state and 2 other state, S1 and S2. So the unroll transition relation will be same as the previous one. So a valid path will have these 3 states. now the important thing is that this valid path should form a loop. So if this valid path form a loop, then we can say that P will eventually hold. So the loop is required because from this state I can reach to this, from here I can reach to this, and I can stay back at here. So I need to check this loop stuff, and if I can identify there is a loop, then I can claim that that P will hold always, because if I have a loop and if P holds on every node in that loop, then I can claim EGP. So what do we do? So we just extend, we just apply, or we do not expand the transition relation, but what we do, we consider one more steps, and just to check whether there is a loop or not. And how we can check this loop? So that means we have to look for the set of states that we have already explored, and if there is a path from one of these explored state to the already explored one. So let's say S3 is the new state, S3 is the new state where I can actually reach, and from S3 does there exist a loop, or from this S3 can I reach to S0, S1 or S2? So S3 is nothing but one of those states, S0, S1 or S2. So if this condition is satisfied, that means there is a loop, because I can reach the same state once again. So this loop constant we need to introduce. So so this loop we just need to check for loop, and on that loop I just need to ensure that P must hold on every state of the path, because if P does not hold, then we cannot claim that G part we cannot actually claim. So the set of constant that we will be writing here, writing now. So initial state, which will be given as A0 B0, so which is 0 0. The transition relations we unfold it twice, and in order to check for the loop we unfold it once more. Fine. And we need to introduce the loop constant, that S3 that I am exploring once more should be one of those state S0, S1, S2, that we can write in this manner. So if it's the same state, that means A3 should be same as A0 and B3 should be same as B0, and this is logical OR. So if any one of this is true, then there is a loop, and the other part will remain as it is, that whether S0 is true here, or this is true, or this is true at this state. So I have to check for P whether this is true at this state or not. Now so this is the complete set of Boolean formula, and we have to check for its satisfiability. And if you check for satisfiability of it, and you will find that this is actually satisfiable, because we can understand from the previous graph that there is a path in which EGP will hold. So therefore the satisfying assignment corresponds to a path from initial state to 0 1 and then to 1 0, followed by a self loop at 1 0. So since EGP is true and I have a satisfying assignment, I have a valid path that satisfies EGP is true, so therefore we can say that AF not P is so this is a counter example for AF, B and A. So therefore this is not satisfiable. Fine, now we will look into that how we can convert this big Boolean expressions into a set. So if you remember the set formula, we need to express in Cnf, and each Cnf, which is a set of clauses, the clauses is set of literals, and each literal will be either positive or the negative propositional variable. So if I have a formula something like this, then we express the formula in this manner. So I missed C here. So this is the representation in the Cnf form. Now we have to convert this Boolean formula into Cnf, and these Boolean operators, if you have other Boolean operators, that can be replaced with negation, or and operator by using the distributive rule and the De Morgan's law to convert into Cnf. Eventually it will be converted into Cnf. We cannot directly convert, eventually it can be converted into Cnf. So one of the brute force approach that we can do, we can construct the truth table, and for truth table will have the set of entries for which something will be true, and for certain of the things I will have an entry F as an output for the Boolean formula. Now if I want to convert the Cnf, then I choose all those rows that produces F in the truth table, and then generate a conjunction of literals and then negate it. So when I choose this one, this, let's say this variable corresponds to B and this is A, then not B and A produces a false, and I would just negate it, this conjunction, then eventually I will get B plus not A as the Cnf form. So this is with respect to one entry, and I have to do for all the entries, and then we have to do a logical AND of all those clauses. So that will give me the Cnf. But the issue with this approach, the complexity will be exponential, because I have to enumerate the whole truth table, and there exists a better approach to address this issue. So the approach that we'll be following is we introduce additional variables in order to convert it into CNF, and we construct a situation where we just check for equisatisfiability scenario. So when we introduce new variables, that effectively means that it is not exactly the same as the formula that we want to express, but what we can ensure that once we create a new formula from the original one, if this new formula is satisfiable, then the old formula will also be satisfiable, and vice versa. So that kind of restriction we can actually make. So let's say, for example, I have been given this Boolean expression, and I can actually convert this in CNF in this way. So when we convert this one, this is a logical equivalent formula of the given Boolean expression. So this is the standard translations and using the brute force approach. Now when we go for equisatisfiability stuff, we try to avoid that exponential factor in conversion. So how we do that? That for every term we introduce a new variable. So here we introduce a new variable e, we introduce another variable f, and we express this one as this way. So this is the by implication, so it's effectively the external operation. So in a simple sense, we can say E is equivalent to A and B, F is equivalent to C and D, and we want E or F. That will be the complete translation. Now I'm just rewriting the stuff. So E or F I just moved in the beginning, and this by implication can be written in this manner. So E implies A and B, and A and B implies E. Similarly for the second part. And now I can convert this expression in the Cnf form, that it will be not E logical or with A and B, that we can convert in this manner, not E or A and not E or B. And similarly for when we convert these to the Cnf form, then I will have not of A and B or E, and when we push not inside or we use the De Morgan's law, we get this expression. And similarly for the other part. Now if you look into the last line, this is the Cnf form that we can actually express. So so the thing is, here we have more number of variables, but what we can actually claim that whenever this is satisfiable, this will also be satisfiable. And if this is satisfiable, then this will also, I can choose E and F in such a way that this is also satisfiable. So the advantage of bounded model checking is that if you use SAT based method, it can explore larger state space compared to the binary decision diagram or the traditional symbolic approach. And since we have a powerful SAT solver, so it's better to use this methodology for checking the satisfiability. So the witness of the counter example that produced are usually of minimum possible length, making them easier to understand and actually analyze, because once we cannot make any comments up to a path length of k, then we actually expand it for k plus 1. So gradually we increase, so it effectively produce the minimum possible length. So there are limitation. The one of the major limitation is it is sound but not complete. Like say that when I say that this is an unset, that means I cannot say whether it is real, whether it will be satisfiable, or whether it is really unset or not, because it is not satisfiable up to k length. But if we increase the path length, then it may be satisfiable. So therefore we need to unfold it to up to the diameter, which is actually unknown on the transition relation, because we determine the transition relation in a symbolic form. The other limitation is that for larger depth you can understand that the number of clauses will will grow very rapidly, and that can create a capacity issue. But the important thing is that set-based formal property verification tool can actually handle larger design as compared to the binary division diagram based tools. But BDD based method is actually complete, but the only limitation for SAT is it's actually not complete. Thank you.